Let us start the big one, the big system of nervous system. Nervous system has three divisions, or rather it can be divided into three parts. The central nervous system, the peripheral nervous system, and the autonomic nervous system. Our main discussion in this particular section is going to be on CNS, the central nervous system. But before we talk about the central nervous system, let me just dwell for some time on the ANS before we start the central nervous system. The autonomic nervous system, ANS, basically when we talk of the nervous system or nerves, they are autonomic nerves and somatic nerves. The CNS will consider the somatic nerves which reach the consciousness, and the autonomic nervous system is the one that controls our involuntary functions, automatic functions, autonomous functions. Now this ANS has basically two branches, the sympathetic nervous system and parasympathetic nervous system. At a very basic level, what we need to understand is which functions are controlled by parasympathetic and how, and what are controlled by the sympathetic nerves. Now first thing is that the parasympathetic system basically controls the minute to minute, moment to moment and day to day functions of the body. That's a division in the sense that it controls regular functions, routine functions of the body. Parasympathetic system. For instance, our resting heart rate is under the parasympathetic control. Secretions of the digestive tract, movements of the digestive tract, all these are predominantly under parasympathetic control. Whereas when the body faces any kind of challenge, any kind of stress, physical, mental, emotional stress, then the major role of sympathetic comes, as if it is sympathetic to the body, something like that. So when you perform the exercise, it's a physical stress, heart rate is increased by the sympathetic system. That's a division. Although every organ system is innervated by both sympathetic and parasympathetic, but this is their function, and they work in a balancing fashion. They keep on balancing each other, and that's how they function. So let us see from where these nervous system operate. Sympathetic nervous system is predominantly called as thoracolumbar outflow. Thoracolumbar outflow, that in the thoracic and lumbar segments. See, if you see the transverse section of the spinal cord, there are the gray matter at the center, the H-shaped area. It has got two horns, the anterior or ventral horn and posterior or dorsal horn. But in the thoracic and lumbar segments, you will see an additional horn, which is intermediolateral horn on either side, of course. There are nerve cell bodies for the sympathetic nerves over here. So sympathetic is mainly called as thoracolumbar outflow. Nerve cell body is located here for the sympathetic nerves. The nerve comes out and immediately synapses in the ganglion. You see that there is a chain of ganglia just outside the vertebral column. So this is the preganglionic nerve. And then the next nerve, the postganglionic nerve, starts from there and goes to the organ. It innervates the organ. So the point is, preganglionic nerve is short and postganglionic nerve is long in the case of sympathetic system, sympathetic nerves, because ganglion is located near the spinal cord, near the vertebral column. Opposite is true for the parasympathetic nerves. In the case of parasympathetic system, the preganglionic nerve, well, first of all, parasympathetic system is called as craniosacral outflow. So cranial nerves perform the parasympathetic function, and sacral nerves. In the sacral segments, there are parasympathetic nerves. Cranial nerves, they are not all of them, just the 3rd, 7th, 9th and 10th. 3rd, 7th, 9th, 10th. These 4 nerves perform the parasympathetic function. Most important, of course, is vagus, is a long nerve, and it moves like a vagabond, therefore probably the name vagus, and that's one important cranial nerve that performs the parasympathetic function. And sacral nerves. Now, what is the difference between sympathetic and parasympathetic nerves is that in the case of parasympathetic nerves, the nerve comes out of the spinal cord and goes all the way to the organ. So preganglionic nerve is long and ganglion is located near the organ or sometimes in the wall of the organ itself. That means postganglionic nerve is very short. That's the parasympathetic nerve. In fact, postganglionic nerve does not have the nerve fiber at all. It's an anaxonal type of nerve. It does not have axon, it does not have nerve fiber. Why? Because it does not have to cover any distance. That's the parasympathetic nerve for you. Preganglionic nerve is long and the ganglion is located just outside the organ or sometimes in the wall of the organ. Another point is that all the preganglionic nerves, they are cholinergic, whether sympathetic or parasympathetic. Preganglionic nerves are cholinergic. They release acetylcholine in the ganglia. Now, therefore, ganglionic transmission is a cholinergic transmission. Postganglionic nerve, so far as the postganglionic nerves are concerned, parasympathetic postganglionic nerves are also cholinergic. They have acetylcholine as a neurotransmitter, whereas postganglionic sympathetic nerves, they are adrenergic nerves or noradrenergic nerves. So in short, the nerve that is ending on the organ finally, nerve that is finally producing the effect. In the case of parasympathetic nerve, it is parasympathetic nerves are cholinergic. Acetylcholine will be the final transmitter on the organ, and in the case of sympathetic nerve, it will be noradrenaline, and so therefore they are noradrenergic nerves or simply adrenergic nerves. That's how they are called. However, ganglionic transmission is the cholinergic transmission, and so far as the receptors are concerned, for the acetylcholine and for the parasympathetic nerves, there are the 2 types of receptors, nicotinic receptors and muscarinic receptors. Nicotinic receptors are of 2 varieties, mainly N1 and N2. Nicotinic receptors are found at 3 places, mainly in the ganglia. So this ganglionic transmission is a nicotinic action of acetylcholine. Neuromuscular junction, where acetylcholine is released, it's a nicotinic receptor, and CNS neurons, wherever there are cholinergic neurons, there would be nicotinic receptors. Muscarinic receptors, 5 types, M1, M2, M3, M4 and M5. These are the muscarinic receptors. Mainly the M3, M4 and M5, they mediate the excitatory effects, and they are excitatory effects of acetylcholine. They are present at various organ systems and they will mediate the excitatory effects. M2 receptors are present in the heart, and they will mediate the inhibitory effects of acetylcholine on the heart. That is why acetylcholine, vagus, the parasympathetic nerve, is inhibitory to the heart. It is exerting its effects via another M2 muscarinic receptor, whereas excitatory elsewhere, because muscarinic receptors are different. These are the receptors for acetylcholine. That means receptors for the parasympathetic transmission. So far as the sympathetic transmission is concerned, sympathetics have alpha and beta receptors, and mainly their division is even the subtypes like alpha 1, alpha 2, beta 1, beta 2, and so on. So these are the receptors. Alpha receptors mainly mediate the excitatory effects of adrenaline. Beta receptors mainly mediate the inhibitory effects, but this is a very generalized statement. For instance, just take the important points, like where are the alpha 2 receptors present? Alpha 2 receptors are presynaptic autoreceptors. Alpha 2 receptors are presynaptic autoreceptors. That is, once the noradrenaline is released at the synapse or on the organ system and it starts its action, then for further release of noradrenaline from the nerve ending can be attenuated, can be modified when it binds with its presynaptic receptor. So alpha 2 is a presynaptic receptor or autoreceptor which will modulate the further release of noradrenaline from the nerve ending. Whereas alpha 1 receptors are present in the organs, and that will exert the effect of noradrenaline and adrenaline. Beta 2 receptors, they mainly mediate the inhibitory effects of the adrenaline. So beta 2 receptors are found in the skeletal muscles, skeletal muscle, bronchi. These have beta 2, bronchial smooth muscle, they have beta 2 receptors. So you can see adrenaline will mediate the inhibitory effects via these beta 2 receptors. For example, vasodilation in the skeletal muscle is mediated via these beta 2 receptors. The blood vessels will dilate. This is the inhibitory effect. Skeletal muscles, you see, sympathetic nerves, they cause vasoconstriction everywhere except in the except at some places. One of them is the skeletal muscle. Skeletal muscle blood vessels have beta 2 receptors in their smooth muscles. So sympathetics will cause vasoconstriction elsewhere, but here they will cause vasodilation. And it's quite understandable because, for example, body is facing stress or body is performing exercise, then muscles need to increase their blood flow. Therefore, there should be vasodilation, and that's mediated by beta 2 receptors. Whereas elsewhere, there are alpha receptors. They will mediate vasoconstriction so that the blood flow decreases to those organs and is diverted to skeletal muscle. So that's beta 2 receptors in the skeletal muscle. They are also there in the bronchial smooth muscle. So beta 2 stimulants will cause bronchodilation. That's the basis of treatment of, for instance, giving salbutamol, the beta selective beta 2 agonists or beta receptor agonists. These are beta 2 receptors. Beta 1 receptors are present in the heart. They will mediate the excitatory effects. So these are some of the points related to the ANS. Now we come to the main topic, and that is central nervous system. Central nervous system will be discussed under 4 sections. We will first discuss the introduction, synapse and neurotransmitters. Then we will discuss the sensory system. In the sensory system, we will have to discuss First, the organization of the sensory system, certain laws that govern the functioning of sensory system, receptor physiology, ascending tracts in the spinal cord, cortex, physiology of pain. After this, we will discuss the motor system. Motor system will have organization of the motor system, functions of cerebellum, functions of basal ganglia. Of course, we will also discuss the descending tracts when we discuss the organization, and then lower motor neuron. Associated with this, we will also discuss the postural reflexes and other related mechanisms in the motor systems, physiology of the voluntary movement. And then the fourth section will be higher functions. So higher functions mainly deal with the cerebral hemispheres, dominant versus non-dominant. Then functions of hypothalamus, a major topic. Its nuclei are always asked in various entrance exams. Sleep and EEG, again an important topic, commonly asked. And various other limbic system, Papage circuit, hemispheres and their functions. So that's how we will deal with the central nervous system. Let us start with the first section, that's introduction, synapse and neurotransmitters. Now, first thing, CNS has two types of cells, neurons and glia. Neurons and glia, two types of cells in the CNS. There are 4 to 10 times more glia as compared to the number of neurons. So glial cells outnumber the neuronal cells in the CNS. We have already classified the types of neurons like multipolar, bipolar, pseudounipolar and axonal. Majority of the neurons in the CNS will be multipolar. And we have also discussed that no new neurons are formed after birth. Only synapses are formed. No new neurons. Neuron is a terminally differentiated tissue. So they do not divide and the number does not increase after birth. The only exception to this is the olfactory neurons. The olfactory neurons continue to divide throughout life. And probably the reason for this is that the nerve cell body of the olfactory neuron is located quite superficially, quite on the outside part of the body, and therefore it is prone to damage on a moment-to-moment basis. As we inhale, there are chemicals and there is friction that can cause damage to the nerve cell bodies. So probably because of that reason, only the olfactory neuron has been given this special capability of dividing throughout life and make new neurons continuously. Otherwise, new neurons do not form after birth. That was about the neurons. We have discussed much of it in the section of the nerves. So let's now talk about the glia, the glial cells, the supporting cells, which is the only cell that is formed outside the CNS and then it migrates into the CNS. The answer is microglia. So let's see the glia. There are two types of glial cells, macroglia and microglia. macroglia. These are the types. Astrocytes. Astrocyte is one type of macroglia. Astrocytes are involved in the formation of blood-brain barrier. Rather, they reinforce the blood-brain barrier. You see, blood-brain barrier is formed by the tight endothelial junctions in the cerebral vessels, and these astrocytes, the star-shaped cells, they reinforce this blood-brain barrier. So astrocytes' function is to reinforce the blood-brain barrier. Second function is astrocytes are involved in neurotransmitter reuptake and redistribution. Once the neurotransmitter is released, then reuptake of that neurotransmitter and redistribution among the various presynaptic terminals is that also is where astrocytes are involved. Astrocytes are also involved in H plus homeostasis and K plus homeostasis around the neurons. So a variety of functions ascribed to the astrocytes. Second type of macroglia, oligodendrocyte. Oligodendrocyte or oligodendroglia, they are involved in myelination of neurons in the CNS. And one important facet which we saw in the previous section is that peripheral nerves are myelinated by Schwann cells and CNS nerves are myelinated by oligodendroglia. But there is one important difference. In the case of CNS, one oligodendrocyte myelinates almost 20 axons. The ratio is 1:20. Now, what is the implication of this? The implication is because one oligodendrocyte myelinates 20 different axons, therefore, after the CNS injury, repair does not become possible. So CNS neurons do not repair because of this one particular fact, that after the CNS injury, there is no intact neurilemma sheath left. One cell had myelinated various axons, various directions, and the sprout, even if it has to grow, it does not get a definitive path to regrow, and therefore CNS neurons cannot repair. So these are the types of macroglia. Second, the microglia. Microglia is called as a scavenger cell in the CNS. It has a phagocytic function. Well, you know, this cell is derived from the monocyte macrophage lineage in the bone marrow, and it comes from that lineage. It goes to various organs, as you know. In the liver, it would be called as Kupffer cell. In the CNS, it would be microglia. So it is coming from out of the CNS. It is a phagocytic function. Removal of the debris after the injury to the CNS is the job of this microglia. So these are the glial cells in the CNS. Let us discuss some neurotransmitters and the synapses. Let's first see the fact-based information, which is the part in the brain that has that it weighs only 10% of the brain but has almost 50% neuronal population of the brain. It's cerebellum. So highest number of neurons in any one part of the brain, it's in the cerebellum. Greatest density of serotonergic neurons is found where? Greatest density of serotonergic neurons is found in the area called as nucleus raphe magnus. Midline raphe nuclei or nucleus raphe magnus has the greatest density of serotonergic neurons. This nucleus is said to be the part of our descending analgesia system. It has got maximum density of serotonergic neurons. Greatest density of noradrenergic neurons is found where? Maximum density of noradrenergic neurons is found in another area called as locus ceruleus. This area is also thought to be the part of descending analgesia system, and it has maximum density of noradrenergic neurons. Greatest population of dopaminergic neurons. Dopamine is the neurotransmitter for reward and addictive behavior. So dopaminergic neurons are found, of course, in the basal ganglia. Nigrostriatal neurons have dopaminergic neurons, and apart from that, there is this nucleus accumbens. Nucleus accumbens has dopaminergic neurons, the D3 dopaminergic neurons. This nucleus is involved in the reward and addictive behavior. So that's dopaminergic neurons. There was one question which is a trick question actually. It's a googly type of a question. Greatest population of orexigenic neurons is found in. Well, why greatest? Only population, only area where orexigenic neurons are found in the hypothalamus. So orexin means orexia is hunger, anorexia is loss of appetite. So hunger producing neurons are in the hypothalamus, orexigenic neurons. Talking about the neurotransmitters, let's see some of the aspects of neurotransmitters. There are two types of neurotransmitters at a very basic level: excitatory transmitters and inhibitory transmitters. Excitatory transmitters, the commonest excitatory transmitters are glutamate and aspartate. Commonest inhibitory transmitter, there was one MCQ like this: commonest inhibitory neurotransmitter in the spinal cord is GABA, glycine, substance P, acetylcholine. The answer was glycine, greatest inhibitory transmitter in the spinal cord. So let's see some inhibitory transmitters in the CNS. GABA is the commonest inhibitory neurotransmitter in the brain, and commonest inhibitory transmitter in the spinal cord is glycine. In fact, strychnine, the poison, is the antagonist of glycine, and it suppresses the inhibition. Therefore, there is excess facilitation of stretch reflexes, resulting in opisthotonous posture. These are the neurotransmitters. An excitatory transmitter is excitatory because it opens either sodium channels or calcium channels in the postsynaptic membrane. That neurotransmitter will be excitatory transmitter. An inhibitory transmitter opens potassium channels or chloride channels in the postsynaptic membrane. So it will hyperpolarize the postsynaptic nerve. That is how it is inhibitory transmitter. This is one basic classification. Apart from this, there is one more way of looking at the neurotransmitters. The neurotransmitters can be classified or categorized as low molecular weight transmitters versus high molecular weight transmitters, which are also called as neuropeptides. Now, all the commonly known transmitters, they fall in the first category, commonly known in the sense that we discuss them more rather. So all our glutamate, GABA, acetylcholine, noradrenaline, all these fall in the dopamine. They are all in the first category, low molecular weight transmitters. The high molecular weight transmitters are neuropeptides, little unconventional types. So we have neuropeptide Y, NPY, orexins involved in the hunger, or opioid peptides, CART. This is a more recently found neurotransmitter, CART. Cocaine and amphetamines regulated transcript, that's CART. This neurotransmitter is involved in satiety. It is thought to play the central role in satiety. So satiety producing neurons have CART as the neurotransmitter. That's another way of looking at the transmitters. What is the basic difference between the two? If you remember neuromuscular junction, our discussion on neuromuscular junction, the neurotransmitter vesicles, there was one question related to it. Vesicle is synthesized in the nerve cell body, but neurotransmitter is synthesized locally in the nerve terminal itself. This is true for all the low molecular weight transmitters. They are synthesized locally, noradrenaline or acetylcholine, all of them. So far as the high molecular weight transmitters, neuropeptides are concerned, that's not the case. The high molecular weight transmitters, neuropeptides are synthesized in the nerve cell body, and then they are transmitted down the axon by the axoplasmic flow. So axoplasmic transport will then transport them. That's the basic difference between these two. Synthesized where? Locally in the terminal, low molecular weight transmitters, and in the nerve cell body in the case of neuropeptides. This was some of the neurotransmitters. Let us see some commonly known neurotransmitters. Let's see some important ones and the disease processes related to them. For instance, let's talk about the glutamate, a commonest excitatory transmitter. Now this glutamate has various receptors. Glutamate receptor is a kainate receptor, one type of glutamate receptor, AMPA receptor and NMDA receptor. Glutamate, its NMDA receptor has been studied in detail. N-methyl D-aspartate receptor, it's been studied in great detail. So what's so special about this NMDA receptor? It's involved in long-term potentiation in hippocampus, the basis for long-term memory, development of long-term memory. This neurotransmitter is, this transmission is also involved in ketamine and dissociative anesthesia. There is the role for this NMDA receptor. So lots of roles have been attributed to the NMDA receptor. What is so special about the receptor? This protein is special because it is voltage plus 2 ligand gated channel, the NMDA receptor. How? Watch this. When glutamate is released and it combines with the receptor portion, channel does not open straight away completely. There is a part opening of the channel. There is a magnesium block on the channel. So that's not completely removed. Partly open channel, and there is a ionic flux. The cations enter through the channel, and therefore membrane is partly depolarized. There is about 15 millivolts depolarization of this postsynaptic membrane, and after that this magnesium block is removed and the channel is opened completely, the gate is opened completely. So it is ligand gated as well as voltage gated. Voltage also is needed to, voltage change is needed to open the gate. Plus there is some action of glycine needed to remove this block on the channel. Therefore, it is voltage plus 2 ligand gated channel. Unique in that sense. This is a very unique type of a channel. What is the disease related to the glutamate? The disease is penumbra in the CNS. What is penumbra in normal language? The penumbra. Penumbra is a shadow, lighter shadow at the periphery is called as penumbra. If you see the shadows, there is a dense core shadow at the center, and then there are lighter shadows at the periphery. These lighter shadows, this phenomena is called as penumbra. The dark dense core shadow at the center and lighter shadows at the periphery. This phenomenon is penumbra. So what is its relation here in the CNS? Penumbra is excitotoxicity to the brain. Excitotoxicity to the brain. You see, it's like this. To put it simply, let's say this is a blood vessel and it supplies this part of the brain. We will expect that when the blood vessel is ruptured, there would be cerebral ischemia and infarct which is limited to this region. That is what is expected. But the damage extends in the neighboring regions. This extension of the damage beyond the original ischemic zone is called as penumbra. So it is something like this. There is a dense core shadow at the center and then the lighter shadow, that extended damage in the neighboring regions. That's the penumbra. The point is why this damage got extended. It's something like this. Cerebral ischemia. Now, ischemia, and we have seen already a number of times that the first thing to be damaged or first thing that loses its function is sodium potassium pump. Anywhere if there is hypoxia, ischemia, first thing that is that loses its function is sodium potassium pump. So cerebral ischemia, there would be failure of the sodium potassium pump, and if there is failure of the sodium potassium pump, that means all the secondary active transports will also fail. Secondary active transports will fail. We have done this already, that all the secondary active transports are critically dependent on the primary active transport, the sodium potassium pump. If the primary active transport fails, then all the secondary active transports will also fail. Over here, therefore, one must remember that glutamate reuptake after it is released into the synapse, glutamate reuptake by the synaptic endings is a sodium dependent symport, sodium dependent co-transport or secondary active transport. So if ischemia has caused failure of sodium potassium pump, then this secondary active transport will also fail. That means glutamate reuptake fails, which means glutamate will accumulate in the synapses, nearby regions. Glutamate accumulates in the nearby regions, in the nearby synapses. It could not be cleared because the transport process has failed, and glutamate then will cause an excessive excitation of the neighboring neurons. Excessive excitation would mean that there would be excessive calcium influx. Glutamate receptor and the associated channel causes calcium influx. So there will be a lot of calcium influx in the neighboring neurons. So much so that the neurons will be studded with calcium, resulting in their damage. So that's the excitotoxicity to the brain, and it's called as penumbra. It's occurring from failure of secondary active transport, the glutamate transport from the synapses. That was some aspects of glutamate. Let us see one more neurotransmitter, GABA, commonest inhibitory transmitter, and the defect related to it, one disease that's called as stiff man syndrome. Stiff man syndrome, SMS. Now, what is the basic pathophysiology? You know, GABA is formed from glutamate by the action of an enzyme called as glutamate decarboxylase, GAD, glutamate decarboxylase enzyme, which forms GABA from glutamate. So, stiff man syndrome is an autoimmune disease. It's an autoimmune disease in which there are anti-GAD antibodies formed. Anti-GAD antibodies are developed. So, no enzyme to form GABA, and that means there is GABA deficiency. No GABA formation. And if there is no GABA, which is the inhibitory transmitter, that means there would be excess facilitation of the stretch reflexes. Excess facilitation of the stretch reflexes. If you have already read this, that upper motor neuron exerts an inhibitory influence on the lower motor neuron. That inhibitory influence is gone. It cannot be exerted because there is no GABA. Therefore, there is excess facilitation of the stretch reflexes, resulting in the hypertonia and stiff man. That's the pathophysiology of stiff man syndrome. Just one additional feature. There is a type of diabetes called as LADA. You see, the normal diabetes mellitus of the type 1 is juvenile onset, which has got immunological origin. But this particular type 1 diabetes, this is a type 1 diabetes, but it starts in late adult life. So it's called as late adulthood onset diabetes of autoimmune origin. This also has the anti-GAD antibodies. It has been observed that even in this is also autoimmune in nature, and anti-GAD antibodies are found even in this diabetes type. So what's common between SMS and this type of diabetes is the anti-GAD antibodies. Therefore, probably it may so happen that all SMSs may also develop diabetes mellitus, something like that, a loose correlation. So these are the neurotransmitters. Let's start with another small topic in the CNS, and that's synapse. Synapse is the junctional region between the two neurons. So it's the junctional region where impulse from the one cell is passed on to the next cell, although there is a gap between the two membranes. Let's take an MCQ at the outset. Commonest type of synapse in the brain is, and the options are axodendritic synapse, axosomatic synapse, axonal synapse, or dendrodendritic synapse. Answer is, of course, axodendritic synapses. Well, at a very basic level, there are two types of synapses. Synapses can be electrical or chemical. let's try to understand that when we mean synapse, it's going to be chemical synapse. Synapse would mean a chemical synapse because in humans or in vertebrates, there are hardly any electrical synapses. Very few synapses are electrical in the vertebrates. Since they are there, let's see 1 or 2 points related to the electrical synapses. What is an electrical synapse? It is like this, that there are gap junctions between the cells, between the adjacent cells, so that there is direct transfer of charges from one cell to the next. That is an electrical synapse, a direct spread of charges from one cell to the next. That's an electrical synapse. Now, how is it different from the chemical synapse? Electrical synapses are faster. They are faster as compared to chemical synapse. Chemical synapse will need impulse to arrive, then calcium channels open, calcium enters, and then the neurotransmitter will be released by exocytosis. That's a chemical synapse. It is little slower. It takes extra time. Electrical synapses are faster, and at least theoretically, bidirectional flow of ions is possible. Theoretically, it is possible bidirectional, whereas chemical synapses are strictly unidirectional. And another important difference is plasticity is rarely seen in the electrical synapses. The modification of transmission of impulse is rarely seen in the electrical synapses. Plasticity is mainly seen in the chemical synapses, and that's the basis for learning. So these are the basic two types. Although electrical synapses are very few, for instance, heart has these gap junctions. Basically, electrical synapse means presence of gap junctions, so that there is a direct spread of charges from one cell to the next. That's electrical synapse. So heart has such electrical synapses, or if we are talking about the CNS, then retina has electrical synapses. You see, retina has these circuits. There is a rod in the retina, then bipolar cell, and then ganglion cell. These cells are connected by the gap junctions. Many of these circuits in the retina are connected by gap junctions, and there is a direct spread of charges. In fact, up to ganglion cell, there is electrotonic conduction. So direct spread of charges, and from one cell to the next, there is transfer through gap junctions. Inferior olive is one place where you find electrical synapses. Inferior olive. Now this is an oval shaped area in the medulla, and what is its role in the CNS functioning? There is an olivocerebellar tract. Olivocerebellar tract from olive into the cerebellum, and so inferior olive shows electrical synapse. Now what is the function of this olivocerebellar tract? Signals coming from multiple sources are collected at the olive, and a single bundle goes as olivocerebellar tract into the cerebellum. So cerebellum is being informed about the joint position or a position of various parts of the body and all that. And it is faster. So note this point. We have done this in the nerve fiber types. A alpha type of nerve fiber is the fastest nerve fiber, and it's used for what? Alpha motor neuron and proprioception. So that fastest neuron is being used for voluntary movements. And even here, something required for the voluntary movements, the olive and olivocerebellar tract has electrical synapse for the faster transmission. So one can say in summary that the man has evolved for voluntary movements, that the fastest transmitting signals in the body are meant for voluntary movements of the body. Right, let us see the chemical synapses. Chemical synapse basically is of three types at a very basic level. Here is a neuron, there are dendrites, and here is the axon. Axon is the nerve fiber which is going to carry the impulse down away from the nerve cell body. So, commonest type of synapse is axodendritic synapse. More than 95% synapses in the brain, in the CNS, are axodendritic type. That means axon of the first neuron ends on the dendrite of the next neuron, and then electrotonically the impulse travels, it comes to the axon hillock of this next neuron, and the first action potential will be generated here. That is the commonest way of transmission of signal from first neuron to the next neuron, axodendritic synapse. These are excitatory synapses, facilitatory synapses. Second type of synapse is axosomatic synapse. 2 to 3% synapses in the brain are axosomatic type. So, axon of the first neuron ends on the cell soma of the next neuron. This, the membrane of the nerve cell body, cell soma. This is axosomatic synapse. This synapse is an inhibitory synapse. This is an inhibitory synapse. In short, when first neuron has to excite the next neuron, the axon will end on the dendrite and there will be a transmission of impulse. When the first neuron has to inhibit the next neuron, then the axon will end on the cell soma. It will be an inhibitory synapse. It is an inhibitory synapse. Cell soma does not have enough number of sodium channels, therefore it can't have the excitatory transmission. What are the examples of axosomatic synapses? There are few synapses of this type. Let us try to understand where you find the axosomatic synapse. One example is in the cerebellum, basket cell on Purkinje cell of the cerebellum. This is an axosomatic synapse. In the cerebellar circuit, there are two main cells. There is a Purkinje cell, and Purkinje cell exerts an inhibitory influence on the deep nuclear cell. Deep nuclear cell sends the output from the cerebellum, which goes to various parts. It will go to the muscles, it will adjust the muscle contractions, it will go to the cortex. Deep nuclear cell is sending the output, but Purkinje cell is exerting an inhibitory influence on the deep nuclear output. It's constantly exerting an inhibitory influence on the deep nuclear output. Now, there is a basket cell in the cerebellum. This basket cell, it gives out a short axon, and this short axon then ends on the cell soma of the Purkinje cell. This is an axosomatic synapse. What is the outcome of this? What is the purpose of this? Basket cell will inhibit the Purkinje cell. This is an axosomatic synapse. The end result is, therefore, the Purkinje cell's inhibitory influence on the deep nuclear cell will be lifted because of this basket cell on axosomatic synapse, and therefore deep nucleus will send the output to the muscles. That is how our muscles are very finely controlled by a switch on switch off type of a signaling coming from cerebellum. Also, a new cell discovered a few years ago, candelabrum cell, is found in the cerebellum. It also forms the same type of, similar type of synapse with the Purkinje cell. What's a candelabrum? It's a candle holder, with candle stand with multiple candle holders. That's a candelabrum. So a candelabrum cell has been found in the cerebellum with this is the stand. It appears like that, and multiple extensions like multiple candle holders, making a synapse with the Purkinje cell. That's one example of axosomatic synapse. Another example of axosomatic synapse is Renshaw cell on the anterior motor neuron in the spinal cord. Renshaw cell on the anterior motor neuron is an example of axosomatic synapse. Let's see how. Here is the anterior motor neuron. Before it leaves the spinal cord and goes to the muscle, it's going to innervate the muscle. It causes muscle contraction. Before it leaves the spinal cord, it gives off a collateral. And this collateral excites the Renshaw cell. There was an MCQ like this. Renshaw cell inhibition is what type of inhibition? Feedback inhibition, feed forward inhibition, collateral inhibition, or recurrent inhibition? The answer is recurrent inhibition. Renshaw cell inhibition is a recurrent type of inhibition. So this collateral, why it's not collateral inhibition? Because collateral is going to excite the Renshaw cell. Renshaw cell is a short inhibitory interneuron in the spinal cord. So collateral will excite the Renshaw cell. Renshaw cell will give out short axon which goes back and ends on the cell soma of that same motor neuron which gave out the collateral. So this also is an example of axosomatic synapse. What is the purpose of this type of inhibitory influence? We will talk about it little later when we discuss the properties of the synapses. But this is a Renshaw cell inhibition or axosomatic synapse. We are looking at the types of synapses. We said maximum are axodendritic and they are facilitatory. Some are axosomatic and they are inhibitory. We saw the example. And the third one is axonal type of synapse. Axonal type of synapse. Very few synapses are of axonal type. What do they specialize in? They specialize in presynaptic facilitation or presynaptic inhibition. That's where axonal synapses come into action, or they are required for these. Let's see how. Here is a synapse, an axodendritic synapse. It's a facilitatory synapse. It's going to cause the transmission. Now, if this transmission has to be modified, one more axon comes and ends on this axon. This then becomes the axonal synapse. What is the purpose of this axonal synapse? It's going to cause something called as presynaptic inhibition. That is, for example, this axon will release inhibitory neurotransmitter and it will cause closure of calcium channels. It will decrease the release of excitatory neurotransmitter in the main synapse. Remember, this is the main synapse. It's for the facilitation, transmission of impulse. But that impulse transmission can be decreased, modified, stopped by the axon that is coming over here and ending on this axon. So this is an example of axonal synapse. Where do we find such synapses, axonal synapse and presynaptic inhibition? This is seen in our analgesia system, descending analgesia system of the body. Descending analgesia system. It works by presynaptic inhibition and postsynaptic inhibition of the pain carrying fibers. Let's see how. Let's try to understand this. Here is a spinal cord and here is a pain afferent coming from the skin, coming from the periphery. It enters the spinal cord and ends there, the first neuron. Second neuron starts from there, crosses the midline and it's going to the higher centers. This is the pain transmission or pain carrying fibers. Now descending analgesia system is going to modify this signal. Uh, there are parts of the descending analgesia system like periaqueductal gray, nucleus raphe magnus. So these are the descending neurons. Now there is a dorsal horn pain inhibitory complex. It does what? It has the neurons whose axons will end here presynaptically. This is a synapse, primary first order synapse. So this descending analgesia system will inhibit this primary afferent carrying pain signals, and in this manner it will cause presynaptic inhibition, or some neurons, they also end on the postsynaptically, that will cause postsynaptic inhibition. We will see that later. But that's the axonal type of synapse with the example. Then a few synapses are dendrodendritic synapse. Dendrodendritic synapses are found in the hippocampus. Very few are of that type. These are the types of synapses. Let us see the properties of the synapses. Properties of the synapses. One-way conduction. First property. At every synapse, there would be conduction from presynaptic to postsynaptic neuron. That's a one-way conduction. Now, in the context of one-way conduction, we need to understand certain terminologies that are used in terms of conduction of impulse. There are a few terms used which we need to understand. What are the terms used? Bidirectional transmission of impulse, unidirectional transmission of impulse, then orthograde conduction, and retrograde or antidromic conduction. Retrograde or antidromic conduction. Let's try to understand what all places do we use these terms. What is the meaning of these terms? Here is a neuron and it makes a synapse with another neuron. Now, if I stimulate the neuron in the middle, what do I get? The neuron can carry the impulse in either direction, in both directions. So a neuron can conduct bidirectionally. That's the first point. Remember, a neuron can conduct bidirectionally if you stimulate it in the middle. Although this is experimental. Normally we stimulate the neuron at its first point, either in the receptor or in the cortex. So that's practical. But theoretically speaking, neuron can conduct bidirectionally if you stimulate it in the middle. But a synapse always conducts unidirectionally, from the presynaptic neuron to the postsynaptic neuron, always, because the neurotransmitter is located in the presynaptic terminal and its receptors are located on the postsynaptic membrane. So a synapse will always conduct unidirectionally. So bidirectional versus unidirectional. Next point. Although neuron can conduct bidirectionally, but what is the meaning of that? Once it takes one direction, then it cannot come back to excite the previous area. This is termed as orthograde conduction, anterograde conduction or orthograde conduction. And onward straight conduction is called as orthograde or anterograde conduction. Once it has taken up one direction, then it cannot excite the previous area. It has to go onward straight fashion. That's orthograde conduction of impulse. Why it cannot come back to excite the previous area? Because previous area will be still in the refractory period, whereas next area is resting, and therefore impulse has to go to the next resting area. It cannot come back. That's called as orthograde, onward straight conduction. And the fourth term was antidromic conduction. Where do you see antidromic conduction or retrograde conduction? Antidromic conduction is seen, one example is cutaneous neurons. In the case of triple response. Cutaneous neurons, in the case of triple response, is, you see, antidromic conduction. Let's see how. What is a triple response? When you stimulate an area of the skin firmly, the skin has been stroked. Here is a skin. Now some area of the skin has been stimulated. You see three reactions there. A red reaction or red line, and then wheal and flare. There would be an edematous formation called as wheal, and flare will be flare up or spread. So leakage from the capillaries resulting in that wheal, edematous wheal formation, and flare is because of the antidromic conduction. See how. This is a cutaneous sensory neuron and its branches, and the signal will be sent to the CNS, to the spinal cord. This is the skin. Now I stimulate the area of the skin over here. Firmly, a line has been stricken or drawn. Now this area is stimulated. It sends the signals via this branch. This is an afferent neuron, mind you. From the branching points, the impulse goes down in the other branches of this neuron. And because the impulse is going in the other branches, there is flare up or spread. So flare is because of this kind of antidromic conduction. See, impulse is going down from the branching point. It will go to the CNS as well, but it is going down in the other branches. This is an antidromic conduction. This is an afferent neuron. It is supposed to carry the impulse from periphery to the center, but the impulse is coming down in the opposite direction. That's an antidromic conduction or retrograde conduction. This term is used in the context of cutaneous neurons. That was the first property of neurons, first property of synapse rather, one-way conduction. Second is delay. At every synapse, there is a delay of 0.5 milliseconds because as you know that this impulse arrives at the presynaptic terminal, calcium channels open, calcium comes in and neurotransmitter vesicle migrates to the membrane, and then the transmitter is released by exocytosis. Then it will combine with the receptor on the postsynaptic membrane, and then impulse will be generated for the next neuron. But this will take some time, and that's 0.5 milliseconds. So more the number of synapses in a pathway, more time will the impulse take to travel from point A to point B. So that's delay at the synapse. The third property of synapse is fatigue. The property goes thus, that repeated stimulation of a synapse for a long time and the neurotransmitter is exhausted. Repeated stimulation, low frequency stimulation, but repeated stimulation for long durations, and the transmission stops for some time. That's called as synaptic fatigue. Transmission stops for some time. Most of us experience this property in our routine lives as well. For instance, imagine there is an exam and we have been studying for the exam day and night. On the previous night also, you have been studying. On the morning of exam, you are reading for the exam, and then you enter the exam hall like this, reading. During the exam, you cannot recall an answer. One answer which was rehearsed well, which was read well, but you could not recall that answer. And after the exam is over, you start recalling that answer again. Why is that? The property of synaptic fatigue. When repeatedly reading and repeatedly utilizing the same synapse, neurotransmitter was being spent. So when you were actually writing the exam paper, in some synapse there was no neurotransmitter. So property of fatigue is because of temporary exhaustion of the neurotransmitter. While you were writing the exam, one synapse did not have the neurotransmitter, transmission could not occur, and you just could not recall that answer. And after the exam is over, after some time, you start recalling the answer again and you think, oh, I just missed that answer. That was because neurotransmitter, which was not there during the exam, is repackaged and it has come back to the synapse. Synaptic transmission resumes again, and therefore you start recalling the answer. So that's because of the synaptic fatigue, and therefore a sincere suggestion would be at least 25-30 minutes before the start of exam, one should keep everything aside. Let the neurotransmitters be saved for the actual exam rather than spending them and coming to synaptic fatigue. Next property is post-tetanic potentiation. Post-tetanic potentiation. Well, this is the property which is the basis for short-term memory. One basis for short-term memory is post-tetanic potentiation. For instance, if I say I give you 2-3 phone numbers and you are supposed to memorize these numbers for some time as a short-term basis, what do? You quickly go through those numbers repeatedly 4-5 times and you remember them for some time. That's the property of post-tetanic potentiation. What is the property? Tetanic stimulation of a synapse. High frequency stimulation for short duration. Tetanic stimulation means high frequency but short duration. Then transmission is actually enhanced for some time. Transmission enhanced for some time. That's called as post-tetanic potentiation. And why is transmission enhanced? That's because of accumulation of neurotransmitter, accumulation of calcium in the presynaptic terminal. You see, the repeated high frequency stimulation of the synapse, with each impulse the calcium keeps coming in, and therefore this calcium is then accumulated in the presynaptic terminal for some time. So thereafter, when the impulse arrives, because of the extra calcium, you all know that's a property of synapse, that the amount of neurotransmitter released is proportional to the amount of calcium present in the presynaptic terminal. So now when the impulse comes, there is extra neurotransmitter released, and extra neurotransmitter released means you recall that phone number which was temporarily stored. So that's the post-tetanic potentiation, the basis for short-term memory. Another basis for short-term memory is presynaptic facilitation. Presynaptic facilitation. There is a synapse with a transmission, excitatory transmission. A third ending or axon comes and ends on this axon. It causes the facilitation of impulse by causing more release of neurotransmitter in the main synapse. That's called as presynaptic facilitation. This is another basis for short-term memory. So that's the property of a synapse, post-tetanic potentiation. Next property is inhibition. Inhibition. Now, there are 3 types of synaptic inhibition: direct inhibition, presynaptic inhibition, and postsynaptic inhibition. Direct inhibition, the example is axosomatic synapses, that the axon of the first neuron ends on the cell soma of the next neuron and it directly inhibits that next neuron. That's the direct inhibition. Second, presynaptic inhibition. What is the basis for this? Decreased release of excitatory transmitter. Decreased release of excitatory neurotransmitter. That's how presynaptic inhibition works. This is a excitatory synapse. It's supposed to cause the transmission. One more axon comes and ends on this axon. so making an axonal synapse, and because of this third axon, it's going to decrease the neurotransmitter release in this main excitatory synapse. It will close the calcium channels, then the neurotransmitter release will decrease in the main synapse. That's a presynaptic inhibition. We have already seen the example of presynaptic inhibition. Endogenous analgesia system works like this, inhibition of the pain afferents. The third is postsynaptic inhibition. Postsynaptic inhibition works like this. Here is an excitatory synapse, the axodendritic synapse, and it's a facilitatory synapse. It's going to cause transmission. Now, one more axon comes and ends on the postsynaptic membrane. How does this work? This will cause hyperpolarization of the postsynaptic membrane. Hyperpolarization of the postsynaptic membrane. So, since this membrane is hyperpolarized, even though excitatory transmitter is released in the main synapse, it will fail to excite the postsynaptic membrane. That's how postsynaptic inhibition works. Even some of the endogenous analgesia system neurons, they work with the postsynaptic inhibition. That's a property of inhibition of the synapses. These are the general types. Let's see two special types of inhibition. There are two special types of inhibition. One is feed-forward inhibition. Feed-forward inhibition. This is seen in the cerebellum. Example is cerebellar learning occurs by feed-forward inhibition. How does it occur? There is a Purkinje cell in the cerebellum, and this Purkinje cell exerts an inhibitory influence on the deep nuclear cell. So deep nucleus output will be under inhibitory control of Purkinje cell. There is another cell called as granule cell in the cerebellum. Granule cell gives out short axons which run to the surface, to the superficial layer of cerebellum, and they make a T, these T-shaped axons called as parallel fibers. They will excite the Purkinje cell, and then Purkinje cell will exert its influence on the deep nuclear cell. Now, granule cell excites the Purkinje cell. If Purkinje cell were to inhibit the granule cell, you would have called it feedback inhibition. But granule cell gives a short axon to excite another cell, a short inhibitory interneuron in the cerebellum called as, for example, Golgi cell. There are three such inhibitory interneurons in the cerebellum: Golgi cell, basket cell, we saw basket cell and axosomatic type of synapse, and stellate cell. So granule cell will excite the Golgi cell, and Golgi cell will in turn inhibit the Purkinje cell. Now this would be called as feed-forward inhibition. Granule cell is going to excite the Purkinje cell directly, but even before that, via short inhibitory interneuron like Golgi cell, it inhibits the Purkinje cell. What is the effect of inhibiting the Purkinje cell? Its inhibitory influence on the deep nuclear output will be lifted, and then deep nucleus will send the excitatory output to the muscles concerned. So this is how cerebellar learning happens in case of voluntary movements, that there is a switch on switch off type or switch off switch on type of output going from the cerebellum, and that's how we make the movements very accurately and precisely. Over a period of time, we learn how much signal would be needed for a muscle to make that movement precisely and accurately. That's a feed forward inhibition. Another type of inhibition is not collateral inhibition, recurrent inhibition. Recurrent inhibition or Renshaw cell inhibition. Renshaw cell inhibition. Now, what is the purpose of this? We have already seen how Renshaw cell inhibition works. Let us try to understand what does it achieve. Here is a spinal cord and anterior motor neuron sending the axon to the muscles to cause muscle contraction. It gives out a collateral just before leaving the spinal cord. It gives out a collateral that excites the Renshaw cell. Renshaw cell then goes back and ends on the cell soma of that same motor neuron which has given the collateral. So, this will exert the inhibitory influence on the anterior motor neuron. Renshaw cell is an inhibitory interneuron. What is the purpose of this inhibitory influence? Let's try to understand this. First purpose is that it delays the fatigue. It prevents the muscle fatigue. That's the one purpose. This anterior motor neuron is receiving excitatory signals from all over. It's receiving the impulses from the reflex arc. It's receiving the impulses from the descending tracts, from the cerebellum. If all those impulses, excitatory impulses, were to go to the muscle, then muscle will fatigue early. And therefore, every time the anterior motor neuron is excited, it also excites the Renshaw cell, and Renshaw cell goes back and ends on the same anterior motor neuron, so that it will create the inhibitory potentials on the motor neuron, its cell membrane, so that instead of 100 impulses, maybe only 60 impulses will reach the muscle, so that the muscle fatigue will be delayed, prevented. That's the purpose of this Renshaw cell inhibition. It decreases the excitability of the anterior motor neuron and thus delays the fatigue. Second purpose of the Renshaw cell inhibition is that it sharpens the signal to the muscle. Sharpening of the signal. Renshaw cell not only goes back and ends on the same motor neuron, the cell soma of the same motor neuron, but it also ends on the neighboring motor neurons, the nerve cell bodies of the neighboring motor neurons, so that when one motor neuron is excited, the other motor neurons in that motor neuron pool, the other motor neurons will be inhibited by the Renshaw cell. The result is signaling will be very, very sharp. Only the correct muscle will be contracted. Even though it is a very small muscle, it will contract. There will be a very sharp signal. No muscle on the either side will contract. A sharp and focused signal. That's another purpose of Renshaw cell. It inhibits the neighboring motor neurons. Another property of the synapse is summation. When one impulse arrives in the presynaptic terminal, it does not create one impulse in the postsynaptic neuron. There is no 1-to-1 ratio. This ratio exists in the neuromuscular junction though. We have discussed this already in the neuromuscular transmission, that one impulse in the one impulse in the motor neuron generates one impulse in the muscle and definitely will result in one muscle contraction. But that's not the case in the CNS synapses. In the CNS synapses, when one impulse arrives in the presynaptic terminal, it generates, if it's an excitatory neurotransmitter, then it will generate excitatory postsynaptic potential, a localized potential of about 2 to 5 millivolts on the postsynaptic membrane, a localized depolarizing potential. So one point on the postsynaptic membrane will depolarize by about 5 millivolts. Now this is not sufficient to reach threshold, and therefore this neuron will not fire the action potential. But Imagine one more impulse comes and one more 5 millivolt depolarization is created locally. Then this is another EPSP which will be added to the first one. This addition is called as summation. So 5 plus 5, it will be a 10 millivolt depolarization. If one more impulse comes and generates one more 5 millivolts of excitatory postsynaptic potential, then it will be added to the previous one. Now 15 millivolt depolarization. Now the neuron will reach threshold and develop one action potential. So the point is, multiple action potentials in the presynaptic neuron. They will create multiple small EPSPs, small local depolarizing potentials. They all will add to form one action potential in the postsynaptic membrane. That's the summation. Let me just also tell you about the differences between EPSP and action potential. Both are the membrane potentials. But what is the difference? EPSP is a localized change, localized depolarization. Action potential is a propagated change. EPSP just happens locally. But when it converts into action potential, then action potential travels through the nerve. Second, EPSP is a graded change. Action potential obeys all or none law. EPSP is a graded response. I mean, just to take the example, just for the sake of example, imagine one vesicle releases its neurotransmitter and that will create 2 millivolt EPSP. 2 vesicles are released, 4 millivolt EPSP generated. 3 vesicles release their neurotransmitter, 6 millivolt EPSP generated. So it's a graded response. It depends on how much neurotransmitter is released by the presynaptic terminal, and it shows gradations. Action potential does not show any gradations. It is all or none. If it develops, it will develop with complete magnitude, complete amplitude, and if it does not reach threshold, then zero response. Nothing in between. But EPSP shows gradations. And the third difference is EPSP is a monophasic change, just a depolarization of 5 millivolts and that's it. Action potential is a biphasic change. So, multiple EPSPs summate to convert into one action potential in the postsynaptic membrane, in the postsynaptic neuron. Now, summation or addition of EPSPs occurs in two ways. One is called as temporal summation. Temporal means time. Temporal means time. Now, this EPSP, which was created, the 5 millivolts EPSP, if nothing happens, then this EPSP will decay over next 15 milliseconds. EPSP decays exponentially over next 15 milliseconds. So the neuronal membrane from minus 70, it had come to minus 65, 5 millivolt depolarization. If nothing happens, it will go back to minus 70 over next 15 milliseconds. So EPSP stays for 15 milliseconds. Within that 15 millisecond time, if one more impulse comes and generates one more EPSP, then it is added to the previous one. So 5 plus 5, that's summation, and it will form 10 millivolt depolarization. If one more impulse comes within next 15 milliseconds, then it will generate one more EPSP of 5 millivolts that will be added to the 10 millivolts. So the point is, within a stipulated time, within 15 milliseconds, if the EPSPs occur within 15 milliseconds of each other, then they are summated, and that's called as temporal summation. The other type of summation is spatial summation. Spatial summation. Spatial summation, spatial means space. Spatial means space. So imagine this, there are 3 neurons and they create EPSPs over the 3 points on the postsynaptic membrane. then the EPSPs generated over this entire space will be summated, and that's called as spatial summation, because there will be a passive flow of currents on this space and those EPSPs will get added. That's called as spatial summation. So two types of summation, spatial and temporal, but just remember that inherent in the spatial summation is the temporal summation. I mean, these EPSPs will be added only if they are occurring within 15 milliseconds of each other. So spatial summation needs the temporal summation, or inherent in it, understood, is the temporal summation. That's the type of summations. Now, therefore, understand one thing very clearly. Neuromuscular transmission had one impulse in the motor neuron generating a large EPP, and that large EPP was so large that it converts, the threshold is crossed by the muscle and it converts into one AP, and it results in one muscle contraction. It means motor cortex had taken a decision to contract the muscle. So therefore, EPP develops such a large amplitude that it will definitely convert into one action potential. So one AP in the motor neuron means one AP, it will call one AP in the muscle and one contraction of the muscle. That's the status there. But in the CNS synapses, that's not how the things happen, because EPP also is a localized depolarizing change and EPSP also is a localized depolarizing change. But the difference is EPSP is of small amplitude and multiple EPSPs have to summate. So multiple EPSPs will have to summate to cause one action potential finally in the postsynaptic neuron. It means what? It means that brain is constantly acting, taking decisions by trial and error. It's not that each impulse is a very definitive impulse, a very goal-oriented impulse. Multiple EPSPs have to add up to form one impulse in the postsynaptic neuron. That's one more property of CNS synapses. And finally, the properties such as occlusion and subliminal fringe. Let us discuss the properties together, these two properties. Subliminal fringe. Imagine two neurons, A and B. These are the presynaptic neurons. And they make synaptic contacts with 4 postsynaptic neurons each. Let us show this in a slightly different way, the 4th neuron. Now, this neuron is making synaptic contacts with the postsynaptic neurons. So, when impulse arrives in A, there will be excitation of 3 postsynaptic neurons. Action potential may be developed there, or 3 neurons definitely excite. When impulse arrives in B, 3 neurons definitely excite. But 4th neuron, when impulse arrives in A, these 3 neurons will excite, whereas the 4th neuron excites just subliminally. Similarly, when impulse arrives in B, 3 neurons excite definitely and a 4th neuron just excites subliminally. But when simultaneously impulse come in A and B, then these 3 neurons, the other 3 neurons, so 3 plus 3, and this 7th neuron also will start firing the impulse. So the combined stimulation of A and B achieves more response than the individual responses of A and B. So that's because the subliminal excitation of caused by impulses in A and B, those subliminal excitations of this neuron, those excitations will be added up. If A and B fire simultaneously, there would be summation, and even this neuron will start firing impulse. That's subliminal fringe. This neuron is said to be in the subliminal fringe of A and B. So that's a subliminal fringe property. Another property, occlusion. Let's say elsewhere in some other scenario in the brain, I am using the same diagram, but it's not the same situation. Situation is different now. When A fires the impulse, it excites 4 neurons, postsynaptic neurons. When B fires, 4 neurons will fire. The 4 postsynaptic neurons will fire. But where A and B fire simultaneously, then 4 plus 4, not 8, but only 7 neurons will fire. There is occlusion of the responses. So, one postsynaptic neuron which was common to both A and B, some neurons which will be common to both A and B, their responses may be diminished if A and B fire simultaneously. So response is occluded or diminished if 2 neurons are firing simultaneously. That's occlusion, slightly opposite to the previous property. These are the properties of the synapse. We have seen the first section in the CNS, that is general introduction, synapse, neurotransmitters.